No, not really, but you can combine things. At this point, it's hard to combine. Because if we make an alcohol, that's one step, but we've never done any reactions with alcohol, so we can't do another step until we learn what we can do with alcohols. I'm not sure where you're getting that question from, probably the workbook somewhere, but let's look at it at some point. Okay, let's take a minute to look back at the, here. Of the two reactions up there, which one gives off the most heat? Which one?
Second.
Second one. Okay, what were your numbers, Connor?
Negative 381 for that one, and the first one was positive 246.
Okay. Delta H equals negative 381. What was that, kcal? Kcal per mole. And the other one was what?
I got 246.
Delta H equals positive
Yes, sir.
246 kcal per mole. Looks like one's exothermic. The one with the iodine is exothermic. So the iodine reaction forms those products plus 381 kJ per mole, meaning it also forms that, but that's released from the system, so it's a negative delta H. I think that's right. Did anybody get any different numbers? Yeah, the one with the iodine is exothermic. So thermodynamically, which reaction is favored? Thermodynamically. One with the iodine. Typically, a reaction that's highly favored, the transition state's not going to be too high, because we're going downhill. Which reaction is endothermic? Well, the one with the F. That's what the numbers say. Which reaction will occur fastest?
Second.
Why the second one, Zach?
It's favored, like it's thermodynamically favored. You don't have to put in energy for it.
No, those two don't go together. The reaction of diamond is thermodynamically favored. The reaction of diamond and oxygen is thermodynamically favored. Are you saying you don't have to put any energy in for diamond to react with oxygen?
Also entropy.
If you don't have to put any energy in, it means it should be reacting right now. But diamonds don't react with oxygen. Your two statements, one was a thermodynamic statement, your other statement was kinetic. They don't go together. What's the answer? Which reaction's fastest?
Why that one spontaneous?
What does it depend on? What does the fastest depend on?
Activation.
Activation energy. Okay, which one has the highest activation energy? We didn't calculate that, but we can guesstimate it, because I just did it. If you're falling downhill, which one are you falling downhill with?
Second.
Second one. How much activation energy does it take to fall downhill? Probably not much. So probably the second one has the lowest activation energy, and probably the answer is the second one. But you can't just say that, because you could be wrong. For example, diamond and oxygen is very exothermic, but it actually has a high transition state, which is odd. So I could be wrong. Really, there's no way to be sure unless you have some exact experimental evidence. But in general, we say it's easier to fall downhill, so probably the iodine. Are the reactions driven by entropy or not? Now, the answer is the same for both. They are. 2 molecules going to 4. That's driven by entropy. Okay? Indeed, the one with the iodine is very exothermic, as calculated, negative 381 kJ per mole. The product is called nitrogen triiodide, Ni3. No, that's the starting material. Ni3, nitrogen triiodide. It's very exothermic. And indeed, it requires very little transition state energy. The only energy that's needed to make this Ni3 go to what? Nitrogen and iodine? All you need is a little tiny bit of activation energy. And all you need is the touch of a feather. It's enough energy to set it off. Once you set it off, it gives off this much energy per mole. That's a lot of energy. Such is explosive if something gives off that much energy. Let's take a look at it. Right here, if you can see, maybe I can turn the light off. Sitting on those two, right there, is two samples of Ni3. It's a dark solid. We're going to touch it with a feather. And when we touch it with a feather, let's see what happens. That's as big as I can make it. You see it being touched by a feather? See that? That's a lot of energy, right? Touching it with a feather, that's a lot of energy. No, that's not a lot of energy. You would think, okay. But it's some mechanical energy there. Gets it over the hump, and then it releases all the energy as an explosion. Notice that the first one's touched, but notice the second one goes off also. That's from the energy it released of the first one, making the second one go off. Okay? That's Ni3. NF3 won't do that. So NF3 going uphill, apparently the transition state energy is huge to go uphill. Okay, very exothermic. But we saw that in the numbers, Connor, yeah? Okay, everybody else see the numbers? Good. My question is, how did they get it up there? How did they put it there? How did you pick it up? Well, if the feather will make it go off, probably your finger will make it go off. Then you'll lose a finger if it's too much. They probably put it up there cold, and then let it warm up, and then they touched it and okay. Oh, by the way, while we're here, y'all gonna be doing polarimetry soon? Yeah, polarimetry, let's put optical activity. Y'all gonna be using polarized light, okay? Some type of light source. There's a polarizer, and it produces TP light, okay? That'll be there. This would be y'all in lab, okay? A light source, polarizer, produces TP light. You'll put the compound in a chamber, dissolved. As the light comes through it, it will rotate it, and then it will hit your eye. And this will be you in lab looking at it. Okay? There's some type of mechanism in here, though, that gives you a reading. Okay? It's not just light coming at you. There is a reading called a vernier, and you'll be shown how to do that. It's in the instructions. Okay? That'll be you when you do polarimetry. You see if your compound rotates the light or not. Hopefully it does, because it shouldn't be a chiral 1 enantiomer for naproxen. Anything else here? It's all the same. Okay, let's see where we're at. Did we find planes of symmetry for the rest of these? I think we answered these three, yeah? How about these three over here? Anybody got it? Are these chiral, achiral, and meso? How about this one here? Anybody got it? Achiral? Well, before I write it up there, I should, I don't know if it is or not. Anybody got something else? Is that chiral or not? Caleb? Brianna? You got meso? Okay, well, meso and achiral.
Is it chiral?
Okay, well, how'd you do this? I would recommend drawing it as a fissure, okay? Unless you have a model and you can rotate it to look for a plane, but hard to see planes of symmetry there. Let's draw that in a Fisher real quick. I'm going to draw it with the chlorines at top and bottom. Why? Because if I'm over here, looking through there, chlorine's going away. Chlorine's going away, the top methyl is towards the hull, it's dashed, so it's on my right. So the top carbon methyl is on the right, there's an H over here. Alright? Now, we want to look at this with that chlorine going away, so I got to come over here, right? With the bottom chlorine going away, the methyl is on my right. H is over here. Now, do you see a plane of symmetry? Boom. It's not chiral. Plane of symmetry. That means the mirror image is going to be the same thing. It is a chiral, but see, that's a chiral carbon. It's got two chiral carbons, so what do we call this?
So,
Yeah, it's actually meso. It's a type of A carbon. Okay, so that's meso. See, that's a mirror plane. I guarantee you if this is R, that's the opposite, because it's mirroring each other, really. Okay, how about these over here? Somebody get this here? Forgot to pass back the quizzes. We'll do that during the break. Taylor? Chiral? Okay, I would do it in a Fisher.
It should be the same.
I would do it, I stand over here, and the methyl going away, and I can draw this. The methyl going away at the top, it's up there. Chlorine is coming out towards you. So if the methyl's going away, chlorine's on my left. I'm drawing what I see. Methyl going away, chlorine's on the left. That means the H is on that carbon is over here. Now I just need to kind of bend my knees and look through here. Chlorine going away. I'm looking kind of straight down it. Okay, I'm above it. Look, and if I'm looking down and that methyl's bold towards you, the methyl's on my left. So with the chlorine going away, the methyl's on the left. And the H is on the carbon over here. What do we see?
First time.
Well, I want to put the methyl down here so it can mirror each other, and then let's look at it. So let's rotate this down. I didn't do anything to the top. When this came down, the chlorine went here, and the H went over here. So now the methyl's mirroring methyl. Two methyls going back mirroring each other. And I'm looking, is this a plane of symmetry? No, chlorine coming forward is not mirroring a chlorine coming forward. There's no plane of symmetry. And no matter how you rotate these things, you'll never find a plane of symmetry. This side is not mirroring this side. And I guarantee you do R and S, they're probably both the same. They're not mirroring each other. So what do we call this compound? Chiral. There's no plane of symmetry. It's, meaning the mirror image is going to be different. Meaning it's chiral. How about the last one? Number two, chiral. Anybody else?
Mirror image of the one.
It's a mirror image of what?
The one we just did.
Is it? Actually it is, because the backbone is the same, and we just changed both. Yeah, it is. It's a mirror image. And the mirror image of a chiral molecule is the other one. They're both, okay? So that's a good little thing to observe there. You can do a Fisher or do it as if you didn't know that one already. We'll just do that. Everybody see why it's chiral and how that was easy to see compared to this one? Because both things were switched. As long as the backbone is the same. These down here. What's this one? There's a plane of symmetry right through here. And so it is it achiral or meso? There's no chiral carbons. That's not chiral. Chlorine H, you get the same this way as this way. So I'm not going to call it meso, I'm just going to call it achiral. How about this guy? Is that a plane of symmetry, bromine mirroring bromine going back? We would need a methyl dash both here to be mirrored. So that's not a mirror plane. How about through here? No, because bromine is not mirroring methyl. Does anybody see a plane of symmetry? No, there's none. That's chiral. No plane of symmetry, so the mirror image is going to be different. How about this guy? There's a plane of symmetry right through here. There's also a plane of symmetry right through there. Two planes of symmetry. And there's also no chiral carbon. That compound is doubly non-chiral, or achiral. How about this guy? Is that a plane of symmetry? No. Br going back, there's nothing mirroring it. But this way is methyl coming forward, mirroring methyl coming forward, half a bromine going back, mirroring half a bromine going back. Do we see any chiral carbons? Yeah, these two are chiral. So even though it has chiral carbons, it's not chiral as a whole. So what do we call it? Meso. These are 5-membered rings that are kind of shown instead of on the board flat, like we may draw it like just like this. You turn it like this. Now it's a 5-membered ring like this. Now this point here, when I turn it like this, the point is now coming towards you. So that's kind of why the point is kind of bolded, as if it's kind of pointing towards you. So that's how that's supposed to be seen, like this. Now if it's like this, substituents, instead of coming forward or back, will be up or down. And so the bromines are shown just straight up. But these bromines are cis, they're both up. So that's cis-1,2-bromocyclopentane. But is it chiral or not? Can I see a plane of symmetry? There is a plane of symmetry. This is achiral. Actually, meso, because it should be meso because it does have two chiral carbons, but it's meso. Where's the plane of symmetry? Well, if I drew it like this, I got a 5-membered ring with 2 chlorines straight up. Do you see the plane of symmetry now? And I don't know how they became chlorine. This is just where it's turned a little bit. The plane of symmetry is right through here. It's just turned a little bit. And right through there, you're cutting between the two BRs. And then as you go through it, you end up cutting through that carbon. It's like this. Just instead of straight on, it's just, okay? So that's an example of one of those where you have to kind of, how could we do this another way? Maybe we were like, I don't know if that's plane symmetry or not. I know it's got 2 chiral carbons. And I know that they're the same. They both have H's. They both have BRs. They both have the same going this way. So it's like, those are the same. Now if we do R and S, it can be difficult here. This is going to be, the H is down. We need to look at it from above. If I'm looking at it from above, I have the BR coming up. Carter with the BR coming this way. So I got one at 12 o'clock. The second one is going to be at 9 o'clock and then 3 o'clock. And the H is going away. That should be S. That's S. I bet you $100 gazillion that that's R. And we have two identical sites that are potentially mirroring each other, because when S looks in the mirror, it's R. And maybe that helps you see that there's going to be some mirroring there, if you can't see it from here. This guy over here, you see a plane of symmetry over there? I mean, obviously you can't cut right through there, because that's a BR going up. We need a BR going up over here to mirror.
It's the odd number of rings.
Do what?
It's the odd number of rings, too, so it's gonna have a problem.
Well, that's an odd number ring. I mean, we can go right through here and there. I mean, you could cut through there like that, just like we did here. The problem is, these are trans. It's like drawing this like that. If you draw it like that, the sides are no longer mirroring. This does not have a plane of symmetry. And I bet if you do S and R here, they're the same. It's like S and S or R and R. This side's not mirroring that side. This is going to be powerful. But those last two are a couple of examples where rings are sort of turned on the side, 90 degrees to the plane.
Is there any type of simple drawing that works for more than two chiral carbons, like the Fisher projection? Or is that generally we use the Fisher for the two and leave it at that?
There's nothing other than Fisher.
Okay. Do you use Fisher for like a 4-carbon chain at all?
I showed you the carbohydrates with the 4 and 5.
Okay. For the chain, okay.
Well, carbohydrates can be open chain or they can be rings, but it's two forms. Glucose has 5 carbons, all adjacent to each other. Okay, so that was those there. Let's do these down here. Number 1, alkene reacted with NCPBA. What does that do to the alkene? Converts it to the epoxide. So in terms of just what we got, we get rid of the double bond and make a 3-membered ring. Okay? But there's stereochemistry here. Stereochemistry. And how did I suggest doing these? Turn it first. I'm going to redraw this. The phenols are cis about the double bond. I'm going to draw this one bold and this one bold. They could be both dashed, but they're cis. And then the methyl, let's put it back. Now we got that alkene turned. See here the phenols are down like my thumb. When I turn it, the phenols are not coming forward like my thumb. Now we have a planar alkene. See, these two are planar. It makes everything planar. Trigonal planar. Now the epoxide reagent, the peroxy acid, can approach from the bottom to the top. If it approaches from the bottom, the pi bond attacks oxygen, kicking off the other oxygen, and then that oxygen back bonds, 3-membered ring. It's going to be both down or both up. So basically, we get rid of the pi bond, and then we make oxygen up. I'm not doing mechanism, I'm doing outcome. But we also get don't change any of this. And that's the power of doing it the way I'm doing it, is we don't change any of that. Because you got it, you either make the O bond up or the O bond down, nothing else, okay? Phenyl 1, phenyl 2. If we make the O bond down, it would look like that. I wish I had drawn this a little bit over here, right under there. But imagine it right under it. And what are these? If that looks in the mirror, what does it see? Does it see this? Those are mirror images. Okay? You see it? There? Mirror images?
Thought the phenols would have to be
Yeah,
going
it was
down
on the,
for it
and
to
then
be
that
a
will
mirror
matter.
image.
The phenols would go back.
No, these are mirror images. Looking down. Pretend the floor is a mirror. If I'm hung over like this and I got my arm out, I'll have a mirror image down there with its arm also out. The arm will also be that way. I mean, the phenol's out, it's looking down and seeing the mirror image and the phenol's out, right? But if I have an oxygen on my back going up, the mirror image will have an oxygen on its back going down. It'll be going away from the body. So the oxygen going away is mirrored by the oxygen going away. You don't see that these are mirror images? If I turn this like this, that oxygen will be going that way, and the mirror image, the oxygen will be going that way. Y'all don't see those are mirror images? Connor.
So this is if the mirror's on the ground, not, if it was off to the right or left, it would be different.
No, the mirror's where I drew it.
Okay.
If that looks in the mirror, what does it see?
That.
I can't hover up there, but it, who sees these are mirror images? Please raise your hand. Okay. I mean, let's just look here. Okay? I'm not going to have the oxygen there. I'd have to make it. Okay, up here. Okay, let's pretend the oxygen's here, and the phenols are red. They're both coming forward, and the methyl's going back. And if it looks in the mirror down there, what will it see?
It wouldn't be.
It'll see, if it looks in the mirror, it'll see, I'm going to make these just both planar. They're both coming forward. If it looks in the mirror, you'll see that one. I mean, you can hold it like that if you want. Hold on. The blacks aren't mirroring. Blacks need to mirror by just switching. Top one, two phenols coming forward and the methyl going back. If it looks in the mirror and the mirror's here, below it,
I think you got the spin the left.
oh, the black is still not mirroring. Because this black is,
Yes, the dash needs to be going down on that picture.
the black,
On the picture, the dash should be going down and it's mirroring the unit.
No, this is in the board.
no, this dash here,
Okay, so it's going back in the hole.
yeah, but it's also going up. Okay, I see a little bit now. See, this dash is really not correct. This dash is really for these to be mirroring, let's look at it right here. For these to be mirroring, the methyl has to be switched, right? Okay, is it mirroring have a help? Oh, well, it's the same thing as if I did it like this, and the mirror was this way. Those are, I need to turn that like that. There we go. They're mirroring. But this is the top one. The two phenols coming forward and the methyl going back.
Really,
And this is the bottom one. Two phenols coming forward, methyl going back. But here the oxygen is down. And these groups are actually a little bit up. There. Okay. These are indeed mirror images. Okay, how could you convince yourself otherwise? Do they have the same connectivity? Yeah. Okay. So they're either the same or they're stereoisomers. Well, you can do R and S. What is R and S here? Here, oxygen 1. Carbon with oxygen is 2. Carbon with all carbons is 3. 1, 2, 3. Methyl is low priority group in the back, so this is what? R. This over here. Oxygen's 1. Carbon with oxygen is 2. Carbon with all carbons is 3. H is in the back, and what is this? S. R and S. What is this? Oxygen 1, carbon with oxygen 2, carbon all carbons is 3, low priority group in the back, 1, 2, 3, what is this? S, and guarantee you this is R. Oxygen 1, carbon with, okay, we're doing right here, carbon with oxygen is 2, carbon all carbons is 3, 1, 2, 3, H is in the back, so that's R. Here we have a stereoisomer where the carbon with the methyl and the phenyl is R. Here we have the same connectivity, but the carbon with the phenyl and the methyl is S.
okay, so we,
Over here it's the opposite. This is the stereoisomer where both chiral carbons have been switched, where all carbons have been switched.
you prioritize.
And what do you call it when everything is switched? An enantiomer, which is the mirror image. So I just proved by doing RNS, yeah, those are mirror images. Question?
On that, I mean, I see why it's a mirror image, but you put the carbon with, why is that one the 2, I guess?
Which one?
Whenever you did the right
Here?
carbon, yeah, prioritize again, so the oxygen's 1.
Oxygen 1, carbon with oxygen bonded to it is 2. Carbon with just all carbon, that's a benzene ring. It's carbon bonded to carbons. This carbon has an oxygen bonded to it. That oxygen is bonded to here also. Okay? Those are mirror images. In the end, all these reactions give mirror images that we're doing. None of these reactions were enantioselective. We said that yesterday. Okay. Those of you, you get, which one of these is favored? I just told you. It's racemic. Okay? It's a 50-50 mix because the reagent can attack from the top or the bottom. There's your product. A lot of times this is showed like this plus an enantiomer. And the person may not draw the other one. That would be the enantiomer down there. If you were asked to draw the other one, you would draw it. Now you could draw this one right here another way. You could draw your backbone the same, that is up, but make the phenyl back and the methyl forward. And over here, make the phenyl back. With the H forward. That's another way to get the enantiomer. But these are the same. Okay? But we did say one way to get to the antimirror is to switch everything, keeping your backbone the same. This is where we didn't switch it. This is where we had just the true mirroring. The backbone was actually flipped. So that's that one. Any questions about that one? Uh-huh.
So enantiomers rotate the polarized like opposite in each. Do non-chiral or meso, achiral or meso ones rotate polarized light as well?
No, they're not optically active.
Is there a reason behind what that, or do we need to know that? What's the chirality is making that?
It's a good question. I'd have to kind of think deeper about it. Ultimately, an achiral compound has symmetry. And that symmetry means there's two parts that are identical. But it also means that those parts are mirroring. And probably the light interacts with this part, and it might get rotated. But the other part's the same, and so it washes out. So an achiral molecule probably almost acts like it's racemic. But it's within the molecule. Where the only time you have just one orientation is when you have this chirality thing. There's no other configuration to make the light go the other way and take it back to zero. And so you end up with a net rotation. How does the molecule actually rotate the light? We're getting into physics and optics and a little bit beyond me. That's a good question though. We did 3 in here. Let's do this one here. Bromine water, what are we doing to the alkene?
No,
What are we making?
forward and back.
What are we converting the alkene to? Halohydrogen, okay, right? You should all know that, halohydrogen. Reactions give outcomes, you gotta start by just knowing what it is, okay? All right? It's a halohydrogen reaction, that's the first. So, I'd recommend turning this, right? Is that the same as the beginning? Yeah, as the first one? We've got phenyl 1, phenyl 2. We got a methyl. There's your stereochemistry right there. Instead of a pi bond, what do these reagents do? You'll get a Br on one carbon, OH on the other. Which carbon is the OH going to be on? Let's see, we get a bromonium ion and then the water attacks which carbon? Most substituted, so the oxygen is going to end up here. Okay? Now all this comes in the plane. Bromonium ion, let me do it. You may not want to write this down. We first may form bromonium ion because we got the alkene. We turned it. Bromine's here, pi bond attacks, it back bonds bromonium straight up or straight down. From that point, the water attacks. The bromine is straight up off of this carbon. How does the water come in?
From the top down.
Okay, if the bromine is straight up, what's opposite?
Down.
Straight down. It comes in straight up the gut here. Okay? They don't come in from the front or the back. You come in straight up, kicking that off. I'll go ahead and do this. Okay, I'll redraw it. So now, we end up with the bromine still straight up. It's just not back bonded anymore. You see, it's straight up. This is still like that. That's still like this. But now the oxygen bond is what? Straight down. I'm going to go ahead and take off the H because I'm not doing mechanism. Although in lots of your mechanisms, the H just disappeared. Okay? You can't just let H's disappear. But I'm not doing mechanism. Okay? But we know we lose an H, and that's straight down, right? Over here, well, this phenyl is coming forward. None of that changes. There's your product after you lose the H from the oxygen. Okay, you're asked to draw it in a fissure, although I don't know why it was 3 to 4. You should do all these non-rings in a fissure. And is this urethra or 3O? Phenyl 1 at the top and bottom. it? Well, you wouldn't ask to draw in Fisher, I don't know why, I noticed that, it should have said 2. Can we draw this in Fisher real quick? Funnel 1 at top, funnel 2 at bottom, so we want this to be the ground. What's going away from me or something in the plane? OH. So if I'm up here, with the OH going away, which side's funnel 1 on? With OH going away, funnel 1's on the left. That means with the OH going away, the methyl's on the right. Methyl. And over here, I can say the bromine going away. What I gotta be careful of is I can't stand like this and say bromine going away because my feet will be in the air. The ground is down here. I gotta put my feet on the ground. And with the bromine going away, the phenyl is on the right. With the bromine going away, phenyl 1, no, this is phenyl 2. Phenyl 2 is on the right, and the other thing there is H. There's the compound, but we were asked to draw phenyl 1 at top and bottom. We can rotate that up and this down. When we put phenyl 1 at the top, the OH goes where? There, methyl swings over here. When we rotate phenyl 2 to the bottom, it's just spinning. Br goes here, and the H comes over here. Now with this top and bottom, is it erythro or trio? High priority group on this carbon, oxygen, high priority group on this carbon, bromine, trio. Plus the enantiomer. How do you get the enantiomer? The enantiomer would come from the bromonium forming from the bottom, and then the water attacking from the top. And if you do that, go through it, it'll also be 3O. But you'll have the OH over here and the bromine over there. So for this reaction, only 3O. You will not get erythro here. So we can ask questions like this. What type of selectivity is that when you get only that one, not the other? It's 3O selective. But in terms of, what's the relationship between 3O and erythro? What's the stereochemical relationship between your stereoisomers? If I drew this with the Br over here, what would be the relationship?
Diastereomers.
Be diastereomers. Erythro and 3O are diastereomers. It's on the table. So we only get this diastereomer and not that. Okay? We say this reaction is diastereo selective. Erythro and 3O is analogous to cis-and-tran. Two diastereomers. That reaction is diastereo selective. Is this reaction regioselective? Yes, the OH is only going to bond to that region. Why? Because the mechanism dictates that. We do not get a product with the Br there and the OH here. Those two products are regioisomers, constitutional isomers. So this reaction is regioselective, right? One other term, is this reaction enantioselect? It's 50-50. Plus an enantiomer, 50-50. Not enantioselective. What did I tell you about the reactions we're doing right now? None of them are enantioselective. All right? So that's easy right now. Of course, nothing over here is optically active, so we don't expect what we generate to be optically active. Why is this not optically active? Because it's a 50-50 mix, it's racemic. Okay? A lot of that, what I just went through, is explained on the last sheet of the stereochemistry page. We alluded to it yesterday. Okay, we did number 3 in class. Number 4 down below, I'll let you do it on your own. If you haven't done these already, we may look at it tomorrow. Okay? Hydroboration, B2H6, the same thing as BH3. Number of things here. So we can end up, is stereochemistry important? Yeah, it's very important. Here's 2 reasons why right here. What's the difference between cellulose and starch? One of them you can eat and the other one you can't. Okay? All right. Starch, your body can digest starch, but it can't digest cellulose. Why? Because the sun rises and heat. If we could digest cellulose, we could eat trees and there'd be no problem with food. Right? But that don't work. What's the difference in the 2? Just stereochemistry. There they are. The only difference is, and these are chair conformations, yeah? Yeah. The only difference is right here, that bond is equatorial coming off that ring, but here it's axial. That's indeed stereochemistry. Because if you do configuration here, one of them is R, one of them is S. That little difference makes huge. Both of these are polymers of a carbohydrate. Okay, individual monomers of carbohydrate. But the way they're connected. Another is, you may have never heard of the drug thalidomide. Back in the 50s and early 60s, especially over in Europe, it was used to treat morning sickness with pregnant women. But at some point, something went bad. Thalidomide was supposed to be one enantiomer, but at some point, the drug company was making it, started making the other enantiomer. And the other enantiomer ended up being very toxic and causing birth defects. And children were being born, babies being born without limbs. No arms, no legs. There's a photo there. They were called thalidomide babies. There was ultimately a nurse in the United States that sort of said that this was what was going on and brought light to the situation. She was awarded a medal by President Kennedy. Take a look at that. Stereochemistry, very important. Okay, we'll get back to alkynes. Any questions about alkenes or stereochemistry though? Well, we'll take a short break. Let me pass out the quizzes and then take a 3-minute break. Let's do this quick. The high on the quiz was a 10 out of 10. The low was, I think, 1.5. If you want to pick it up here, please yell. Devin? Joe? Here. Barbara,
Here.
Elena,
Here.
Scott, Kayla, Taylor Gandy, Lauren McCaspin, Aaron Mazzetti, Josh, Kelly, McGetchy, Shayna, Marco, no name, Melissa. Myron? Lauren? G? Shelby? Utah? Lucy? Sophia? Ashley?
Here.
Michael?
Here.
Amanda? Robert? Taylor? Barnett?
Here.
Blake?
Here.
Michelle? Andrew?
Here.
Shakira?
Here.
Aaron? Caleb? Josh?
For certain songs, you say we don't know, is that only in lyric or not in brains?
For it to be stereogenic in a ring, it has to be a huge ring.
So if it's in
And
like
we didn't see any,
lows,
we didn't see any examples.
okay, so if it's like lows and there's alkenes, then it's stereotypical.
Not necessarily. Possible.
So you're saying like an answer or whatever?
No, you have to know if the alkene is stereogenic. We did some of the alkenes.
So that's all alkenes,
If your alkene, alkene nomenclature. That alkene is not stereogenic. You can have different things. Neither is. But that alkene is.
because the alkene there, you have two possibilities.
Okay, so it's possible, but you'd have to determine if it's the same.
Yeah, the alkene, and usually the rings we see, there's not, because the ring, if that's making a ring, it can't be trans, you wouldn't be able to make a ring. Unless it's huge.
That's our,
What's that?
what we're our new material for the testing, and we know everything we need to know.
I don't know about that, but hopefully you know everything you need to know.
I mean, you're the one teaching us, so.
Yeah, but I'm not the one learning, I'm not the one learning.
For this.
Looks like your methyl is bonded to the ring carbon. If it's bonded to the ring carbon, what's the oxygen doing? The oxygen is bonded to the ring carbon. Look at the product. The oxygen is bonded to the ring carbon. Okay, guys, alkynes, we're looking at Roman numeral 3, addition of water, hydration of an alkyne. Most of these reactions, just like alkenes, just twice the fun, right? Yeah? Okay. Let's ignore the mercury. I'll tell you, okay? You can do the mechanism, let's just ignore it. I'm not going to use it. But we know with mercury, with an alkene, mercury can react and you can get a hydration product with mercury. It's traditionally just kind of put in there, and you'll see it in textbooks, wherever. But you get the same outcome as if it's not there with your alkynes. And in fact, when you do it in lab next week, you're not going to use mercury. But you will see it in textbook and everywhere else. All right, we got H plus in water, right? I saw a lot of trouble with the mechanisms. Arrows going, I don't know where they're going. Every time I use an arrow in a mechanism, I start by saying what? These electrons. Okay, I don't start by saying this atom is going to move here. I don't start by saying this charge is going to move there. These electrons. And usually I'll circle the electrons I'm talking about. It's harder to circle a pi bond electrons. But I try to do it as if I'm hinging it. Okay? These electrons, are they going to pull away from the left carbon or right? They're going to pull away from the left. So I'm going to sort of pull them away. Over here. Pull it away and go attack the H. Okay? Somebody pull my arm. Pull it and go attack the H and go make a bond to H. It's kind of simplistic. But for some reason you guys just have tons of trouble with it. I don't know why. What does this give? Which carbon now has a new bond to H? The left one or the right one? That one over there. See, I think you think that carbon's bonded to the H. No. This arrow is not meaning, I'm not talking about that carbon when I show this arrow. Because that does not show what the atoms are doing. It shows what the electrons are doing. The electrons are breaking away from that carbon, going to attack the H. I'm pulling them away. So this carbon over here bonds to the H, leaving that carbon over there without the bond, and that carbon over there is less the positive charge. 1, 2, 3, 4. Don't lose track. Got 4. 1, 2, 3, 4. Actually, 5 carbons. 1, 2, 3, 4. 5 carbons. The new H is bonded to the 5th one. There's one H there to begin with. Now there's 2. sorry?
How do we get it? Can't this should still be linear, right?
It should still be linear, you're right. There's still a double bond here, and that's plus. Yes, that's still SP, that's still linear. You're right, it still should be linear. As soon as something attacks it, it'll then be SP2, like trigger. Okay, what attacks it? Does anything back bond?
No.
No, because the new thing doesn't have any lone pairs. It's a true cation. Now water attacks it. All right? I saw a lot of this on the quiz. It looks like a plus charge attacking the water. I don't know what it means. Because what we want to show is these electrons attacking and making bond to there, just a covalent bond. What does that give? All right, you can draw these H's in if you want. So now we have bonded here oxygen. All right, I saw a lot of this. What does this mean? The carbon's bonded to the H? Okay, that's not descriptive though. Bonded to the oxygen. The oxygen is bonded to it. That's what that shows. The oxygen has two H's. I would draw them out fully covalent. How many lone pairs on the oxygen now? One, because the other lone pair made a bond. Now this happens to be a charge, because it's not a natural or a typical oxygen. What's the charge? Positive. We learned how to do charges on week 1. Okay? And you, as you do your mechanism, you just anticipate charges, okay? Oxygen bond makes 3 bonds, it's going to be positive. There we go. Now, there's got to be a minus here. If there's H3O plus, let's say the minus is HSO4 minus. Now, something's got to take an H. On the quiz, I saw just all of a sudden it only had one H here. Well, you've got to show the H being lost, because the H, okay? That's your mechanism. You don't just lose H's out of the blue. Where does the H go? This takes, now this I told you, I'm not going to show this full Lewis structure with a lone pair. Some of you tried to show Lewis structure for that. It's okay. I didn't count off of this, but a lot of you tried to show H bonded to an S or something. Well, that's not right. In sulfuric acid, the H is not bonded to the S. The H is bonded to oxygens. But as I told you, with this type of guy, I will usually not identify the lone pair. But some lone pair, see if you drew it out, it would be that. And then this attacks, makes bond to H. These electrons move on to oxygen. And now we get this thing called an enol, and we reform sulfuric acid, which is essentially what the catalyst was, H+. It comes from sulfuric acid. It's okay for me if you just show this doing this, and not identifying the lone pair there. Because that's the way I do it on the board, because it just takes so much time to draw that out. So that's okay. But I saw a lot of this where this H just going over here. That's not right. Okay, so there's the enol, and there's really nothing new there.
What about the mercury? What is that?
I'm not going to use it. You'll see it in the textbook. I'm not going to use it in the mechanism. Okay? Now, when we did HBr or something, we then turn around and add it again to the double bond. And if we added water again, see this reaction, the H plus is still there. Let's do this. How do you get the ketones in? This is new, odd. It's really not a big mechanism. It's pretty straightforward. Let's act like we were just repeating this and add another water, okay? We have H+, we reform sulfuric acid, so, which we know is really ionic, even though I reformed it. Can this react with H+? Yeah. Now, alkene. Are we only plus on left or right? Left. So these electrons hinge away and attack this, and we get what? Plus here, new H there. Just where we were, like if we were just repeating what we did over here. What do you see?
Oh, no, sorry, I was just,
No, that's a very hydride shift from where?
From
From the OH, and make it O positive?
Well, we'll make a.
No, we're not gonna make it O positive. This is a cation. Now, if we were going to add water again, what would we do? We would have another water, and we would add to the cation. But that's not what happens, because we don't end up with two oxygens bonded here. But we can also think of this. Which electrons are closer to this plus? These or these? Those. Let's move these in. What does this give? That gives double bond to O, but there's an H there. One lone pair positive. There's a new H here. I'll draw it in. And what did we just do here? What do you call this that we just did on the board? Resonance. Okay? These are resonance structures, double-headed arrow. Resonance structures. We've done this, this is at least the third or fourth time we've done this. We did it yesterday with the chlorine. The chlorine moved in and did a resonance. So instead of water attacking, we get the oxygen. Look how close we are to this. There's a new H there. Let me draw it in for you. What do we need to do now to get the final product? This can take the H, leave this behind. You get that, and what do we reform? We reform our acid. So getting this odd-looking product, a ketone, is the mechanism that odd? Oh, hopefully not.
so tautomerization is not an internal process?
Do what?
So, tautomerization is not an internal process. You need to have like a...
Internal process?
Right, so it doesn't just rearrange by itself into...
What do you mean rearranged by itself?
Like have chlorine in it. make
Yeah,
it
so
double
you-
bond.
What?
When, on the previous one, we had chlorine and it produced that double bond for the resonance. That would be like an internal rearrangement, so for that, it's interacting with other molecules to give off the ketone.
I don't understand the question. The only difference between this and yesterday was we just had a double bond to chlorine. I mean, this may have been different. We just had this, right? Did we have something like this yesterday?
Yes.
Double bond to chlorine?
So why would it
You wound up with two chlorine.
The double bond was
Now, we had double bond to chlorine yesterday, right?
Yes.
Yeah? So what's the question?
Would the oxygen do that? Like, that double bond attacks the H on the oxygen and took the H down, and the O would have a negative charge, and those electrons move into make a double bond. Would that be possible since the chlorine rearranges like that?
Well, it's not a rearrangement.
For the residents.
But we did the same thing here, we did residence with the oxygen.
But you have an outside molecule with water going in instead of dechlorine.
We had another CO.
Where's the outside molecule?
You're talking about having the water going in.
I said this could attack here, but instead,
Oh.
this attacks. I asked you which is faster to put electrons in, here or here, which is gonna be faster?
Then-
That, we didn't do this.
Okay.
Can you use water instead of the H2SO4?
You can always use water instead of the, yeah. Because how does H2SO4 exist in water? Hydronium ion, H3O plus. See, over here, when we did this, this cannot go neutral by losing an H. And so over here, we ended up adding this another Cl minus, essentially here, moving this up, and we ended up with 2 chlorines, right, yesterday?
Yeah.
But this can lose an H and go neutral. And when it does, that's actually your product, a neutral and a ketone. Okay. What did we do here? We hydrated the triple bond, made an enol. We didn't hydrate again. We didn't add water again. Instead, we did this rearrangement. And I called it a rearrangement, but Sarah said, that's not a rearrangement, here to here. The entire process is a rearrangement. This is resonance, and resonance is not really anything. This is pink. I just showed you red and white. But if it's pink, it's pink. It's not two different things. Okay? The process, these are isomers. I showed you the formula. This formula has H2O added to it. 2 H's and an O. We've added water, we hydrated. These have the same formula. We're not adding water, we're just rearranging. These are constitutional isomers. But this type of constitutional isomer is called a tautomer. Tautomers. And the process of going from one tautomer to the other is called tautomerization. What is the definition of a tautomer? Constitutional isomers that only differ by what? What's the difference in these two?
The pi bond
In terms of atom connectivity. This H has moved from the oxygen to the carbon. Has any other atoms moved or relocated? No. Now we did make a pi bond change. Here's the definition of a tautomer. Relocation of a single hydrogen. And at least one pi bond. But when you change the pi bond, you're not relocating atoms. Tautomers only differ by relocation of how many H's? One. If the two structures you're looking at have 2 H's or 3 or more than one relocated, they're not tautomers. These are tautomers. The process is called tautomerization. What we showed here is the mechanism for the tautomerization. What's the first step of the mechanism? Tell me what this step is called. Call it 500 different things. Tell me what you want to call it. What do you want to call this step? Terminology is important.
Hydration?
Here to here is not hydration, because we did not add water. What did we add? H minus or H plus? H plus. When you add an H plus, what do you want to call it? What would you just do? If I had paint to the wall, I'd say I painted the wall. What do you want to do here? You added an H. H is also called proton. We protonated the enol. Okay? Terminology. Protonated the enol. To give this, what do we then do? On the board, we invoke resonance. That's really not a step, okay? But it's something we do on the board or on our paper. Then what did we do? Well, we went from here to here. Let's see, I removed an H plus. Deprotonated. You protonate, you do resonance, and you deprotonate. That's all we did in this tautomerization mechanism. Now, I have another name for what we did first. We protonated, but I can also say this. We put proton on. Everybody agree we put proton on? There it is. Okay? Proton on. We then did resonance, and then we did proton what?
On.
What?
Off.
Off. On, resonance, off. Now, how do you remember that? Oreo, like a cookie. O, R-E-O. On, resonance, off. That's your mechanism for tautomerization. It's your mechanism today, it's your mechanism near the end of event 2, it's the mechanism, okay? Oreo. Do you want to do tautomerization? Oreo. Are we under acidic or basic conditions? Acidic. If you're under basic conditions, the steps of Oreo are reversed because bases don't put protons on. See, acids put protons on. What do bases do? They take H's off. If you're under basic conditions, Oreo stands for off, resonance, on. And we'll do basic conditions maybe here, but definitely in organic too. Okay? Hopefully Oreo is a good way to remember your tautomerization mechanism. How many steps in this mechanism? 2 steps. What are the 2 steps? Putting the proton on and then taking it off. You put it on the carbon because that's where we need it, and you take it off the oxygen because you want to take it off. Resonance is not a step. We do it as a step on the board, but it's not. Okay? We call this like red and white, but the true color is pink. As soon as we put the proton on, we got pink. And then we take it off. Okay? It's really only 2 steps. Resonance is not a step. Only on our paper is it a step. All right, that's tautomerization. Good way to remember it. Tautomers. Which of the following are enol forms of the compound in the box? With enol being a tautomer. Which are tautomers of the compound in the box? Is this a tautomer?
Yes.
Is this a tautomer?
Yes.
Is this a tautomer?
No.
No. Is that one?
No.
No.
It's the same.
Are those 2 the same?
Yes.
Okay. I must have just doing something. Why is this not a tautomer? Because what's the difference? If we draw in our H's, there's how many there? 1. 1. There's 1 there. Drawing these H's. Oh, there's 2 there. There's 2 there. And I'm not going to worry about the methyl because there's the same in both. And I'm not going to worry about it over here. Okay? And going from here to here has only 1 H moved. Hold on. There's also an H here that's new, right? Okay. Can you go from here to here and only move 1 H? No. It looks to me like, how many have moved? 2. And not tautomers. Tautomers where you relocate from just 1 H. And a pi bond. Usually for carbonyls, your tautomers are enols. Which ones of these are enols? See, these are enols. The OH is on the ene. An alkene with an OH on it. Usually your carbonyl tautomers are enols. But I reckon there could be some partner that's not exactly enol. 1H. Only 1H moves. Okay, let's do this. Let's try BH3, hydroboration. If we hydrate this by this method, you'll see the oxygen is really going to end up on the N carbon. Because, what is the pi bond attack? Yeah. I saw some on the quiz, this attacking something down here. When you have 1 and 2, this is done like 1 week. That's done like 10 years later. 2 totally different steps. Okay? This is not combined. It's like 2 totally different reactions. It's one process, and some people may call it this is a step. It's a single reaction that consists of 2 sort of steps. It's just big terminology. Okay, we attack the boron because it has the empty p orbital. So these electrons are going to break away from the left carbon and attack the boron, leaving carbocation on the left carbon. You got to keep track of your carbons here. There's a 5th one. 5th one's bonded to boron, and it has 3 H's. It happens to be a negative. One, 2, 3, 4, 5. 1, 2, 3, 4, 5. There's a double bond here remaining. But this here is what? Positive. But is this really formed, or does something happen at the same time?
It's gonna 1,3 hydrogen.
This boron shoots one of these H's off. These electrons break away and move over here. And that gives double bond with the BH2. That's neutral boron, and now the new H is here. And by the way, these are going to be cis. Because that is fixed. It can't rotate with a double bond. Why are they cis? Because if the boron is up, the H has to be up because it's thrown from the boron. So all that's consistent. Now what does the magic step do? This is in step 1. Now the magic step does what?
Change that pH to OH.
Replace that with OH. And now what is this? That's what we drew. When we do the magic replacement. So there's your enol. But what do enols do? And we didn't say this before. Enols are not stable structures. Enols will always tautomerize to the carbonyl form. Instead, you want to have carbonyl here, and this H ultimately moves where?
To the carbon without double
It's going to be over here. If you do it mechanistically, you start with H+. Hold on. We're under basic conditions. We'd have to do the tautomerization under basic conditions. Let's do it under basic conditions. What's the first step under basic conditions? Off. Off, resonance on. It's reversed. What H do you want to take off? The answer is easy. The one that needs to be taken off. Which one needs to be taken off? The one on the oxygen. Indeed, isn't that one the most acidic? When you're ready to make it, okay? These electrons take the H. These electrons move behind. And we get what? O minus plus water. Acid-base reaction. We could judge an equilibrium if we had pKa's. We're not going to worry about it. It's going to go to the right. After we take the H off, now what do we do? Resonance. Okay, I don't think we've ever seen resonance of an anion. First time. We'll see it many more starting tomorrow or next week. We do resonance. these electrons, one lone pair is in a p orbital interacting with this p orbital. We can show resonance by this moving here and this moving out. Resonance arrow. What does this arrow movement give? This is making pi bond to oxygen. How many lone pairs left on oxygen? Just 2. That's a neutral oxygen now. Now when this came down, this means the pi bond is moving out onto carbon as a lone pair. And that's now a minus. This is a resonance structure. An alternative Lewis structure. So we did O, re, what do we need to do now? Now we need to do on, because we started with off. We need to put a proton on here, because there's 2 there. What can supply a proton? We're not under acidic conditions. What can supply a proton?
Ion.
Water can. These electrons can take an electron from proton from water. These stay behind. That gives this. There's now 2 H's here. Why is an H shown there? Because there's 1 there. And I just like to show in the H's of my aldehydes. And what do we also form here? We reformed hydroxide. Hydroxide is thus, by definition, a what? Catalyst. So your tautomerizations are catalyzed either by acid or base. Before we did an acid catalyst, when we reformed acid, here we did basic catalysis and we reformed base. All of this is sort of an equilibrium, except that's not an equilibrium. But one thing we need to say, I kind of said it, is your carbonyl form is the favored form. It's your favored tautomer. Your enol tautomers are not stable. They will always tautomerize. In organic 2, we'll see some that do not. What do the brackets mean? When you see brackets and such, it means it's not isolated. That it's formed, but then it continues on and does something else. You'll never isolate it. You're never going to like distill an enol and go run an IR and say, this is my enol. No. Because as soon as it just keeps going. Never isolated. Questions about tautomerization?
Could you see tautomerize without encapsulates?
Theoretically, you can do any reaction without a catalyst. Where the catalyst just speeds it up.
Right.
But some reactions are so slow that it doesn't happen without the catalyst. So it's a tough question to answer. Also think about this. When would you ever not have an acid or base around?
What's it going to use?
Superglue is a liquid. To get it to become hardened, you have to have a catalyst around it. If I put superglue right there, what would it do? Yeah. That's because there's acid or base right there. It's impossible to have no acid or base around. Everywhere. On your fingers. In the glassware. Okay? So the question is very theoretical. Okay. We're not going to do other reactions like epoxides and cyclopropanes, because you just don't do those with alkynes. It's mainly like HX, and then like chlorine, Cl2, and then hydration. But when you hydrate, the enol is your intermediate, and the enol does the rearrangement to the carbonyl form. Do we need to memorize that a primary is a terminal alkyne, gives an aldehyde product? No. to show the product. It is an aldehyde. Okay? All right, the next reaction will be reduction or hydrogenation. We did this with alkenes, adding H2 to the pi bond. You can also do that with alkynes. Hydrogen and a precious metal catalyst, like nickel or platinum. And how do the H's come in? Syn or anti? Syn. So if we add two H's, sort of like the metal, and H here and H here, okay? This is not really a mechanism because we would not show movement of atoms. It's not mechanism errors. What do we get? It pushes these up, and the two H's would be down, right? So this makes sense. But that's what I got drawn right here. Right? The two methyls are cis. I just got it flipped over. So this makes sense. But look, this is still a pi bond. It's still an alkene. And alkenes react with H2. And it's just going to do it again. And when you do it again, you end up with the alkane. And now with the alkane, it has free rotation all the way around. And so there's nothing to really show there in terms of stereochemistry. So we can do it all the way, and we would have H2, and we would say like 2 equivalents, and like nickel or something, we need 2 equivalents. Or sometimes you may say 2 atmospheres. That implies that but really you need double, you need 2 moles. And this means we don't stop here, you go all the way. Okay. Now, chemists would like to do all possible outcomes. What if we wanted to stop here? How could you do it? You can stop there if you use what's called a poison catalyst. And we would call this partial hydrogenation, not complete. Partial, we would get a cis alkene because we know the H's come in from the same side. And we can stop there. What is a poison catalyst? It's where you add something to the metal, like a dope, it's called a dopant. Dopant is where you add something to change it. There's lots of things that will modify the reactivity of the catalyst. For example, if you add barium sulfate to palladium, that'll be a poison catalyst. It won't be as strong, and it'll allow you to stop here. There's one called Lindlar's catalyst. It's kind of a convoluted, it may have 2 dopants added to it. But what I want to tell you is, whenever you see Lindlar's catalyst, that's a poison catalyst. Okay? And the poison catalyst stops here. Cis. Well, how can we go from an alkyne to a transalkene? Meaning we want the 2 new H's to be opposite sides. Can you do that with hydrogenation? You can't, because they always come in from the same side with hydrogenation, even with a poison catalyst. How can you stop it at a trans? You can do that with sodium and ammonia. This is going to be a new reaction. This is actually a radical reaction. First look at a radical reaction. Let's look at this. And this is our last page of the material here. Stuff down here, acid-base chemistry. How does this happen? This is sodium metal. I can put a 0 up there. Oxidation state of 0. This is ammonia. Ammonia here is both solvent and reactant. Minus 33 degrees. Why that temperature? Because at minus 33, ammonia is a liquid. And this is done in actually liquid ammonia. The liquid being your solvent, so it's a liquid solution. And minus 33 probably comes from putting dry ice in some type of other solvent, and it achieves minus 33. It's very common to see minus 78. That's where you take dry ice and put it in acetone. If you do that, it'll be minus 78 degrees. So the minus 33 is, it's not just random. It's easily achieved. Okay. If you dissolve these two react to produce what's called solvated electrons. What do we know about sodium? Does it want to gain electrons or lose them? It wants to lose how many? It wants to lose one. Why?
So it'll be stable.
Because it's on, it'll be like the noble gas that's over there if it loses one. Okay? I like to lose an electron. If you put it in ammonia, it will lose the electron to the ammonia. But what is formed? It's actually known to be, or thought to be, just a free electron. And the ammonia is just sort of solvating it. Okay? A little bit of hand waving, what's really going on here. But it also turns a bright blue, color of Zach's tennis shoes over here. What are the tennis shoes in? Or Joe's, is it Joe? Joe's t-shirt. Put sodium and ammonia, it'll turn. And that's the solvated electrons. Okay? You can read about it, what they want to say about it, and they show a photo in the book. See a photo online. You can probably find a video online of somebody adding sodium to ammonia and it turned blue. Okay? But what we have is, we have electrons. Now I'm going to show this as like that. Alright? Like a free electron. Alright? Now what happens is the free electron adds here. This is opposite, because usually this is attacking something. Here the electron, I think I do need a dot, because we're going to start showing dots up here. The electron pumps in, these two carbons are identical. Doesn't matter which one you do. We throw it in here. Now importantly, because we're only moving one electron, it's a single unpaired electron. We're only moving one electron. And when you move one electron, you use a fishhook arrow, a half hook. Because every other time we ever do an arrow, we're moving how many electrons? Lone pair, or a bonding pair. This is the first time we moved a single electron, fishhook, and if we throw, something has to leave this carbon. Well, these two electrons move over onto the carbon. And that gives double bond, single electron here, and here, and then this moved over as a lone pair, and you get something that looks like this. Single electron and a lone pair of electrons. What's charges of each carbon now? That carbon's actually minus. What's the charge of that carbon? Neutral. It's charge of an electron.
Negative.
Minus. If a minus reacts with a neutral, you should get a minus. Well, there it is. Now, why did I draw these groups trans? Why not draw them Which do you like better?
Electron stream.
Here it has a choice. When that comes in, the groups can go cis or trans. Which is going to be preferred?
Trans.
Yeah. See, here you have a choice and the best wins out. That's why you end up with trans at the end. If we're doing a hydrogenation with hydrogen, does it have a choice if the H is coming in either the same side or opposite? No. Whenever you bring in H2, it's always the same side. This had a choice and it went with trans. Okay, what do we need to do to get from here? Well, we got to pick up H's. Where do the H's come from? There's only one H source. It comes from ammonia. Ammonia serves as an acid. Well, that's odd because usually ammonia is a base. But that's a very strong minus. These electrons take an H, these stay behind. This is the acid-base mechanism we looked at on day 3. Okay, what does that give? We now have what here? H plus NH2, 2 lone pairs minus. Still got this up here. By the way, what do you call it? Something that has a single electron that is not paired. Radical. Okay? It's a radical reaction. Intermediates are radicals. All of our other intermediates in previous mechanisms were not radicals, they were what? Here's an example of one. This wasn't a radical, it was a ion. Before we had ion intermediates. That's a radical intermediate. It's a radical reaction. Okay, let's keep track of that. At this point, actually another electron gets pumped in. And we get two there. It's no longer a radical, and now it has a charge. Now it's minus. Now it's ready to pick up another H from ammonia. And so now we have another ammonia. These electrons take that, stay behind, and we get that. Put our other H on. And what do we form again? Okay. Ultimately, you pump in your electrons from the solvated electron, and then anions pick up H's from ammonia.
So this says that a charged carbon is favored over an uncharged one that has a radical.
Tell me where? This,
Right, so that would be,
it pumps in and make an anion?
right.
Well, that's the theory, that's the mechanistic theory. That's the leading theory. It's sitting at a point for someone else to come along and come up with a better theory. What type of evidence is there here? You have to, there's probably evidence for this, but this is the leading mechanistic theory. Okay, importantly, let's balance this equation. That reacts to give that plus what? What did we form here?
2 NH2.
Form 2 of those. What was the fate of the sodium metal? What did it become? What does it become when it gives up an electron?
Positive.
A positive sodium. Yeah. How many of those did we make?
2.
Yeah, we had to give up one electron, and then this implied another sodium, so we made 2 positive sodiums. Well, guess what? Each one sits with this. There's a positive sodium that sits with that, and there's a positive sodium that sits with that. Now that can be shown just formula. We made NaNH2, plus and minus. How many of these did we make?
2.
2 of those. Now it's bound. How many sodiums do we need if we want to completely balance this?
2.
And how many ammonias? Now it's completely balanced. 1, 2, 2 gives 1, 2, actually. Because each one of these
Because the 2 hydrogens on
has both in it. But it should be balanced now. Ultimately, the sodium and the ammonia will be formed in a Questions about this mechanism? First look at a radical Fishhook arrow when we're doing a single electron, pumping it in. Very kind of amazing and wondering, wow, fascinating reaction, especially the color. Let's try to finish this page up down here. Acidity of terminal alkynes. The H on a terminal alkyne is pK about 25. It'll be your most acidic of your hydrocarbons. It's more acidic than an alkene, more acidic than an alkane. Why? Because the resulting anion is stabilized. Why is that more stable than just something like that? Hybridization effect. Right? Because this is SP, it's 50% S. Okay? Actually, if you look back at the acid-base handout, I discussed that right there with the hybridization, right? Look back at your acid-base. Look at the acid-base, the pKa's in the back of your lab manual. Terminal alkynes have enough acidity that we can do chemistry. What type of bases will remove that H? N-butyl lithium. What is that? It's actually another carbanion. It's straight chain butyl and a lithium plus. But this is more basic than that, so that will take the H. These electrons take the H, leave that behind. We make that plus butane. pKa 25, that's 40. Which side's favored? 25 or 40? 40 is favored. So N-butyl lithium will do it. NaNH2 will also do it. That's what we formed in the previous reaction. The nitrogen will take it and will form ammonia. The sodium will sit with the minus. Ammonia has a pK of 35 as an acid, 25, which is favored. 35 is favored. So that reaction will work. Please, when you see this, what's the charge of the sodium here? Positive. Do not confuse that with sodium metal and ammonia. It's not sodium metal, that's Na plus, nitrogen minus. But you need to know some Lewis structure for the nitrogen. Understand that it's minus. How do you know the nitrogen is minus? Because sodium is plus. Question, is sodium hydroxide strong enough to deprotonate terminal alkyne? And we'll finish up 2 to 3 minutes here. If we showed the reaction, this is organic chemistry. Let's get rid of the spectator ion. Minus, we make this plus water. Sodium can sit with that minus. Water is 16, this is 25. Which side's favored? This side. So is hydroxide strong enough? No. But those bases are. Those are stronger bases. Actually, the reverse reaction is favored. If you take these are often called acetylide anions, because the 2 carbon is just acetylene. But your sp carbanion will actually take an H from water and go that way. That's the favored route. Because of that, we'll end right here. Just an interesting thing. Back in the 1800s, the miners used to wear helmets that had a flame up here. Before they had batteries and flashlights, they have a flame. The flame would come from having a calcium carbide. Calcium carbide is an ore. You drip water on it, you make acetylene, and as it produced acetylene, they would light it, and it would burn controllably and have a continuous flame on your hair. Not hair, but helmet. Helmet. Of course, if they were using hairspray or something, they have potential corrosion. That's why they used to do mine. Also, they had handheld kind of lamps like this. But this here is calcium carbide. And what happens when you put this in water? Takes an H, so you end up with H's here. And when you put H's there, what do you now have? Acetylene. And acetylene we know is like for torches. It's a gas, it can be burned. So that's an application of that, the reaction going the other way. Okay, guys. Lots of material, summary, yeah? Hopefully it's presented in a way that you can use your knowledge for the problems. Tomorrow we'd like to start the material, but I'll also, at the beginning tomorrow, answer any questions you have. Okay? That's the end of the material.